Hi everybody, thanks for joining my talk about running a DevOps-style production Docker cluster using the Microsoft platform. My name is Loek Duys and I work for a small Dutch consultancy firm called Xspirit as a cloud architect. Over the past few years, me and the team have been working on a project for gas storage. So if you dig a hole in the Netherlands and you go down about 2 kilometers, you will find that there's a big hole somewhere near the coast. So that hole used to be filled with natural gas, but the Dutch gas company, well, they withdrew that gas from the bubble and sold it on the market. And then they were left with this big bubble, big empty hole. So a clever energy company from the Middle East decided that they wanted to purchase that hole and use it as a storage facility for natural gas. So what they can do now is use it as a sort of parking garage. So in summer, when gas is cheaper, you can purchase gas on the market for a lower price and then store it within that bubble. And then in winter, when the gas price goes up because demand is high, you can take the gas out of the bubble again and sell it on the market. And you can make a profit by the difference in price. Well, this clever energy company also offers this as a service to their customers. So it allows the customers to either withdraw or put in gas. So the deal with this system is that it's a time-critical system. So there's very little buffering in the gas network. So what is being pumped into the network at one end must be consumed at the other end. So it's very critical that whenever a customer decides that it's time to pump out gas, that it actually happens on that moment in time. The demand varies over time, like I already mentioned, but it also varies over time during a working day. So for every hour, customers indicate how much they either want to inject into the bubble or withdraw from the bubble. So just to give you an idea about what this plant looks like, it could supply about 6 million households for 1 year, or it could supply the entire country for about 2 months. It holds 8.4 billion cubic meters of natural gas. The amount of energy that it's capable of producing is more than a nuclear plant. So these are really huge numbers we're talking about. Well, when we came in, we were asked to replace an earlier system. The way that worked in the old days was by doing monthly deployments by a dedicated operations team. Whenever the software was deployed, they would go to a server, log on to that server, and use a USB drive to copy binaries, the new binaries, onto that system. During that operation, the system was offline, and if there was an issue, the process had to be reversed manually as well. There was very little telemetry gathered from the system, so whenever there was something wrong, they usually found out by customers calling them on the phone and explaining that they couldn't do a certain action. So that meant there was no proper way to detect whether the system was healthy or not. Everything was running on a single machine and there was a dedicated server. So that server could be considered a pet server because everything that was on there was installed manually, and whenever it was broken, it had to be taken out for repairs. And whenever it needed to be changed, it could take a couple of days for that change to be implemented. Whenever there was an outage, it needed to be dealt with manually. The system experienced frequent crashes. So what happened, obviously this system, it communicates with the customers and it also communicates with the Dutch gas company. So whenever one of those connections was broken, the system didn't deal with that very well. So what happened? The system could crash, and it would crash regularly. The unfortunate bit there was, whenever it did crash, there could be some data loss, and that could mean that customers did not get the injection or withdrawal they requested. So that was a bit of a problem as well. So when we started working on this system, we thought long and hard about what we wanted to do in our weekends. Because, we were on call for this system, and that meant that we were the ones being called out of our beds in the night and being called into the office on the weekend. We thought long and hard about how we wanted to deal with this. And the result is, among other things, this presentation. So we decided we wanted to stay at home in the weekends and play with the dog instead of being in the office and taking care of a system. To find out how, I'll let you know. So we obviously cannot demonstrate the entire planned system here, but I can show you a simplified version of the system. The simplified version has a single page web app as a front end. And this front end, obviously you have Mark front end, and it handles customer requests for injection and withdrawal. The front end sends its requests to a backend, and that's an ASP.NET Core Web API. And this takes all these customer requests and summarizes it in the background, because, if one customer decides he wants to inject some gas and the other customer decides they want to withdraw the same amount, then the plant doesn't have to do anything. The network is just balanced as it is. That brings me to the last component of the system, and that is the plant API. And this actually steers the real plant and either requests injection or withdrawal. So let's have a look at that system. This is Visual Studio 2019, the system we used to build the platform. And let me start here with the storage transaction control. So whenever a customer decides he wants to inject or withdraw some gas, it ends up here. And this transaction is processed obviously, and while it's being processed, the system returns a HTTP status code 202, which means accepted. You can see it over here. And it returns the transaction identifier, and the customer can use that transaction identifier to query the status. If you look at the transaction processor, it is a hosted service which is built in .NET Core. And the nice thing about a hosted service is that it can run in the background, and it runs for the duration of the lifetime of the web platform itself. So whenever the application starts, this thing starts, and whenever the application stops again, this thing will stop as well. So what you can see here is, as long as cancellation is not requested, so the stop function is not called, we will go into a loop that continuously tries to process any pending transactions from that store. The way that looks is by going over them, summarizing all the customer injection and withdrawal requests, which indicates, after calculation you will know whether to inject or withdraw something from the bottle. And you submit that to the client by sending it a flow instruction. And for that we use an HTTP client and just simply submit that flow instruction to it. Excuse me. The way this looks in real life is something like this. So I can, as one customer, I can decide to inject something, and as the other, I can decide to withdraw something. And you may have noticed this indicator here, it will follow whatever the people want to do. So if I inject one more and then withdraw one more, it should end up at 84 again. So just to give you an idea about the size of the system, the way the system works, let me just inject 6 more. And we will expect this to go to 90, but in fact there's something wrong, and what that is, we'll find out later. But first, what do I mean with DevOps style? Well, DevOps is probably familiar to a whole bunch of you, but what DevOps means to us as a team, it means autonomous teams and shared ownership. So we, as a development team, we work best if everything is within our sphere of control. So we would like to control the way the infrastructure looks like. And this is why we decided to use the cloud. Because whenever you use the cloud, you can define your infrastructure as code. And you can deploy it from code as well. We'll see that later. We want shared ownership. So we not only build the code, but we also run the code. So whenever there's something broken, it will be us that is responsible to make the changes to the software or the infrastructure to fix the issue. Well, to do that, we want to automate everything, because nothing is more tedious than creating resources in Azure all day. So whenever we decide we're happy with something, we reverse engineer it and we create scripts, so the next time we want to deploy something, it will be automated. We chose to use an iterative approach as well. So instead of first building the entire system and then asking for feedback, we decided to use an agile approach and get feedback as early as possible. And by this means you can know whether you're taking the right direction earlier than you would if you get feedback after the process has completed. So if you apply this process to a mission critical system, then a couple of additional rules come up. Well, don't worry, I will show you a little bit about every one of these in the coming presentation. So the way we tackle this problem is by dividing it into a couple of different segments. So first, let's have a look at the way we deal with the development and delivery process. If you look at a typical enterprise architecture, you would see that many of the development teams are grouped around technology. So you would have teams dedicated to user interface. You would have teams dedicated to the ESB. You would have teams integrated to SAP and Siebel and DWH, data warehouse. So what that means is that in the typical enterprise architecture, the teams are grouped by technology and the people are grouped by profession. And what that means is that whenever you want to make a change, for example, if you want to change something in the data warehouse, maybe add some columns there, then you would probably have to talk to people in ESB to get the information there. You would have to talk to people from business services and to people in the user interface teams. And all of these teams would have their own agendas and their own deadlines and their own busy schedules. So it means that every change you want to apply to this system could take a really long time, because all the teams need to be synchronized. Well, an analogy for this problem is this view that you see here. So what you see is that all the parts of the engine you see on the background are grouped by functionality. So this means that it's logical cohesion, and that means that you're grouping by things that are the same in nature. We've already noticed that to apply change to this makes it very, very complicated. You have to talk with all the other part owners in order to make a change. Well, what if you change the way that stuff belongs together and instead use functional cohesion? So again, have a look at the background picture, and all of a sudden you see an entire engine block now. And that means that, obviously there are a couple of interfaces to that engine block. You need to apply to adhere to some rules in order to keep this engine compatible with the car. But inside the engine, you can change anything you want. You can make changes to all the stuff that is not connected directly to other systems. And that means that you get immense freedom of choice all of a sudden. So this is what functional cohesion is about. That is grouping stuff that contributes to a single task. If you apply that to your software delivery teams, then you get something like this. It means autonomous business capabilities. So instead of grouping by technology, you group by functionality. So you have one team that is responsible for the dispatching, or the system I just showed you for injecting and withdrawal gas. And you can have a different team that deals with the data warehouse. And these systems are all connected by a service bus. So they can change independently and they can change internally as much as possible. And the only interface they have to the outside world is also standardized, which is the service bus interface. So these teams are now designed for change. And whenever a team wants to change something internally, they do not have to communicate with any of the other teams outside of them. So it means you build it and you run it. So you're both responsible for the delivery of the software, but also for the maintenance of the software. So remember the lack of telemetry from the older system. So they didn't have a clue whether it was working or not, except for when an angry customer was on the phone. So let's have a look at how you can fix that problem. A modern phrase for this is shift left, and that means that you want to gather telemetry as quick as possible in the development process. So telemetry can come from not only the software itself, it can also come from automated testing. It can come from fire drills, so you know your disaster recovery procedure is okay. And you can get telemetry from your delivery pipelines as well. So let's have a look at more details. Let's have a look at gathering telemetry from the application and zoom in on these aspects. So if you remember, I showed you that the system crashed earlier. So in fact it's still reporting an error. Let me just fix that in a second, because obviously that bug was staged and it was all to give you this nice view. So this is application insights on the Azure portal. I've opened up the live metrics tab on application insights, and what you can see here is that, well, the system is obviously broken. You can see that requests are taking a long time, and every few requests there is an error, and the error is a weird bug that has been encountered. So let's have a look at what we can do to get more information about that. The way I usually do that is by going into the application map. And well, you can already see that about 90% of the calls from the back end to the plant system are failing. So it's not an issue in the front end. The front end is fine, but the back end cannot communicate with the plant. That is the issue there. So let's have a look at one of the exceptions that occurs. You can already see that the system was running fine until I started my demo, and now all of a sudden it's generating a lot of exceptions. So let's zoom in to one of those exceptions and see if we can find out what's wrong. You can see some more details about the environment that this system is running on, and in this situation it's the production version of the plant system. So let me just collapse this and make this a little bit more readable. So what you can see is that the backend system is calling the plant system, and it takes about 10 seconds and it does about 2 or 3 calls there. And well, obviously they are all failing. So these calls are grouped together and something is going wrong. Well, what happens there is this. The transaction processor is trying to submit instructions to the plant system. You can see that I'm adding custom telemetry to monitor the performance of this call every time. What you do not see is the retry behavior. So obviously the system was doing 3 calls before it crashed, but you can only see 1 call here. What happened there? Well, to do this I'm using an HTTP client generated by Refit, and augmented by poly.net. And poly.net allows me to add retry behavior to an HTTP client. So I just inject a regular regular interface for the API. This is just a planned client. But the way I create the concrete instance of that object, that's a little bit special. So let's have a look. Obviously, first I need to get the planned endpoint from my configuration, and that means the HTTP URL under which I can call the planned system. And then you can see me creating a retry policy and a timeout policy. So my overall timeout will be 10 seconds, and that corresponds with the information we just saw in Application Insights. So I'll give my planned client 10 seconds to perform the process. During that 10 seconds, I will try the call with a 5 seconds timeout. So if there's no reply within 5 seconds, it gives me time to do one more call, and if I'm lucky, maybe even 2 more calls within that 10 seconds. I wrap those policies together and I add them to the primary HTTP client I'm using. So I'm adding the HTTP client here, adding the retry policy there, and apply that to the refit generated REST API planned client. Alright, well, let's see what more we can get from our application. Well, obviously we saw a lot of errors being generated and that was easy to find. But it's not always errors that are causing issues. There could be some more vague issues as well. So if you compare these two images, the left system is the healthy system and the right hand side system is the unhealthy system. So what you can see is that in the earlier version of the software, the CPU was fine. It was running about, well, 30-40% of the CPU, which is fine. So there's room for any spikes that may occur, and the system is quite happy. What you can see after the delivery of the new version is that the CPU becomes very erratic. So sometimes it's at 0%, sometimes it is at 100%, and overall it's very hard to plan your resources according to this chart. What you can also see is that the request rate was going strong at about 300 per second. All of a sudden it dropped all the way to almost 0. And the call duration, it was really low, it was in the millisecond range, and all of a sudden it becomes in the second range. So you can see that you can have issues in your system without exceptions, and this is why telemetry is very important. Okay, well, suppose you do have an issue, and these issues also occur in the night when you're very groggy and you just woke up from a nice dream, and well, you try to remember what you needed to do when SQL Server had an issue, for example. And this is why we have runbooks. So the runbooks will help you decide what to do in case of a predictable issue. So SQL Server, well, it is a fact of life that whenever you use SQL Server, especially in the cloud, you can have some outages. So during a week you would have, well, probably 1 or 2 minor outages. So SQL would be unavailable for maybe a few milliseconds. So whenever a millisecond error occurs, you don't want to be called from bed. But if it takes more than a couple of seconds, then you want to get alerted. And then it probably becomes time to deal with the issue. And maybe you want to fail over to a secondary SQL Server instance running in a different cloud region, for example. This is called failover. So whenever you want to do that in the middle of the night, you want to make sure that you're doing it right. So this is why runbooks exist. We created runbooks for these situations. So the runbook will describe how you would do that, how you do the failover bit, and of course who needed to be informed as well. And finally, if it doesn't work, who you can call to help you with the process. Another form of communication of issues is the status overview, the system status overview. So we decided to use the tool status page for this. And what it does, it simply displays the health of your system. And it doesn't display it just to you, but it also displays it to your customers. So whenever your customer is using your system or trying to use your system and they experience an issue, well, the first thing in the old days they would do is get a phone and call the gas company. But what if they could have a nice web page that already displays that there is an issue, and it also displays that you're already working on it. So your customers can just have quick feedback about your system. They already know that you as a service deliverer are aware that the system is broken, and well, they don't necessarily feel the need to give you a call and notify you about the issue. So this gives you as a ops person a lot of freedom to deal with the issue instead of having to deal with phone calls all day long. So I already mentioned it is important to automate stuff. Whenever you do something more than once, it's probably already worth it to automate that stuff. So to do that, obviously you deliver your code in an automated way. So by using Azure DevOps pipelines, for example, or Jenkins, whatever your favorite tool is. But you can do the same thing with infrastructure as well. So if you're using the cloud, in our case we are using Azure, you can use Azure Resource Manager templates to deploy infrastructure from code. So you define what the infrastructure should look like, and then by using a delivery pipeline, you can deploy that infrastructure. You can also you can also do your failover behavior from an automated fashion. So what we did was we created Azure DevOps pipelines that did the failover process for us. So the DevOps pipeline is not really delivering software or infrastructure in that matter, but it was responsible for a repeatable way of doing failover by running PowerShell scripts. We decided we wanted to have a bot in our Slack channel as well. So the Slack channel is where all the developers meet and talk about the issue that is currently at hand. And there's a bot in that channel as well. And you can talk to that bot and ask it to, for example, to restart a node or a virtual machine whenever there's an issue with that machine. So instead of having to do that manually, you can ask a bot for it. And the nice thing is because all the team developers are in that Slack channel, they can all see, well, this step has already been taken by another person, so I don't have to do it myself. So it's a way to communicate during an incident, managing the incident, and to get some work out of your hands at the same time. Well, finally, obviously your code needs to be unit tested, so that's an easy form of automation there as well. And during that build on the build server, you can also perform some static and dynamic code analysis. So you can test for code quality, but also for security issues, for example. Well, you can have a nice way to fail over to your secondary environment, but if you need to find out that it works whenever things are really broken and it's an emergency situation, that's probably too late. So the shift left paradigm also applies here. You need to make sure that your failover scripts work before they are really necessary. So what we did was we would do a failover and a failback at least once a day. And if everything was happy, it just kept on running and nobody would even notice that we did a failover. But we, as the DevOps team, we would have a lot of confidence in the failover procedure. So we weren't worried at all to run that procedure in the middle of the night on a Sunday either. So you already heard me talk about pipelines quite a bit, but well, let's have a look at continuous delivery and get some more details about how we approach this. So we decided to package our software in containers. We did that because containers are portable, and the old saying, it works on my machine, in this situation it usually also means that it works in production. So it's a really nice way of packaging up your application together with a platform and store that as a container image in a registry somewhere. The nice thing about that is that whenever you get the image from the registry, it just works. And if you get that image and deploy it to multiple machines, you get to scale out as well. So it's a very comfortable way to scale your software. We decided to run our containers on a Docker cluster. Specifically, it's an Azure Kubernetes service cluster. So using Azure Kubernetes allowed us to scale the cluster up and down quite easily. So scaling out, it means that you just add a couple of machines to the cluster and then you're good to go. And this is all automated, so AKS will make sure that the new machines are prepared properly and that the workloads can be shifted there as well. So this allowed us to scale the containers up to nearly unlimited volume. It also allowed us to do controlled releases. So the way this works is by deploying our new software version to the cluster, but not switching the network connections to it yet. So what we would have is like the new software version deployed next to the old software version, and then we can run some tests on the new version before deciding, well, yes, let's reroute the network connections to the new version and take the old one out of commission. That gave us a lot of, a feeling of security. So whenever there was a problem that only occurred on production, which was very rare, we would still be able to deal with it before it was actually taken in production. So you separate the release of the software from the deployment of the software. Also, AKS or Kubernetes in general has automatic healing. So that means whenever a container crashes, it will be restarted automatically by Kubernetes. So if a system encounters an unhandled exception, for example, well, it crashes, but not to worry, it will start up on a different location likely, and it will become healthy automatically again. Well, in return, I have to admit, it did bring us a lot of complexity. So to get a good working feeling with Kubernetes or AKS in general, it takes a bit of time. So there's a learning curve there, and you need to be prepared for that. So let's have a look at the way we deploy those containers to the cluster. So what you can see here is our delivery pipeline, software delivery pipeline. So it starts on the top left, and we will first deploy our software to the test environment. Whenever it works, we will promote it to the failover environment. And finally, if that works, we can deploy it to the production environment as well. So the important thing to notice here is that we deploy the same image version, in this case the 1.0 version, and we deploy that to every environment. And we change its behavior by specifying different configuration. So we do not generate a different image for the test environment, different from the failover environment and different for the production environment. No, same image, and it gets promoted from different environments. Obviously, this whole process is monitored, so we get instant feedback whenever something is wrong during compile, during unit testing, during image generation, or during deployment. So we have a complete insight of the entire process, the entire workflow it takes from source code to production. And once this deployment is complete, you're ready for the next. Well, let's have a look at how we deploy infrastructure now. I think it will look quite familiar. So what we did was we take our ARM templates, we put them in the Git repo. Whenever an ARM template is changed, well, a new commit is made to the repository. The build pipeline will be triggered just like in the software, and we will just deploy those ARM templates using tasks and PowerShell. So the first thing we did was to switch the active environment to failover. So instead of running on the main production environment, we're after this running on the failover environment. So production is no longer in use, and that gives us the opportunity to deploy the new infrastructure to the production environment. If we're happy, we can start using that production environment, freeing up the failover environment, so we can deploy that infrastructure there as well. So again, during this, the system is never offline, and whenever there's a failure, let's say the deployment to production doesn't work, we still have our failover environment happily running. Okay, well, let's have a look at redundancy. I've already mentioned that this system is a mission critical software system, so it needs to be online at all times. Well, the big problem with having a single point of failure becomes clear if you take the Star Wars Death Star analogy. So the Death Star was destroyed, and then the entire empire collapsed. So what they should have done probably is just create two Death Stars instead. So one could take over if the other one fails. Excuse me. So in our situations, we are running our software in both the EU West Azure Cloud and EU North Cloud. So whenever the EU West Cloud is having a problem, then we can always fail over to the North Cloud. And whenever that has a problem, we move stuff back to EU West. Well, a Death Star is nice, but it's still one big point of failure. So what you want to do instead is think about that change-enabled system I talked about earlier and move towards autonomous business capabilities. So instead of having this big Death Star, you would carve it up into different fighters, and each one of those fighters would have its own specific functionality. So now, if you lose a fighter or one of them breaks up, then all of a sudden the other ones can continue working, because they're all autonomous and they're all happy to run without the presence of the other. And by this way, you can make your system even more solid. Well, you heard me talk about failover environment quite a bit, but what does that look like, that failover environment? Well, in our case, it was a smaller version of the original. And it doesn't mean that it had fewer resources. No, because we needed those resources and that could not be tampered with. No, the smaller version means that it had fewer functional items. So we had a discussion with our customer, the person who paid us to build the system, and the customers they have. And we sat together and we talked about what is the most mission critical system of the entire platform. Well, obviously invoicing and reporting, those are not mission critical. If reporting is down, that's fine for a couple of hours. But the delivery of gas, the asking for withdrawal and injection by the customers, that is the mission critical bit. So that is the part that we made our failover environment for. So instead of moving the entire system into the failover environment, we chose to deliver only the most essential parts of the system there. And also the autonomous business capabilities helped us to do that in quite a simple manner, because the other systems, there's no direct dependency to those other systems, so it's fine to run just a couple of them. So it's now time to flip and go into a little bit more technical bits, and that is how to create resilient software. So let's look at a couple of ways you can cut dependencies inside your system and cut dependencies to other systems. So the first one well, you may realize that you've already seen this one. It's called the retry pattern. And let's have a quick look at that application insights portal again. And this is really the retry pattern at work here. So instead of failing at the first attempt to call the planned API, we try for a couple of times before failing. Well, in this case, I created this exception, and the exception is permanent, so retrying doesn't make a lot of sense. But if this was caused by a deadlock, for example, or a transient error, that means an error that will go away in time automatically, it does make a lot of sense to retry that. So if you have a deadlock in SQL Server, for example, and you retry your transaction, then there's a good chance that it will work again. So the same thing applies to this system. So what we do is whenever there's an issue in the plant API, we can check the error code that we get in return. If it's a service unavailable, we can just retry again. But if it's a permanent error, like a bad request, we don't need to bother. Retry is often combined with a circuit breaker pattern. So the downside of retrying calls to your database or your backend API is that it takes 10 seconds now. And if you have a million users in the system at the same time, those million users would all have to wait 10 seconds for the system to become healthy again, or to report that it's down. You probably don't want that. So if one customer encounters a fatal issue in trying to communicate with a remote system, it could flip a circuit breaker instead. And then that circuit breaker, like a bridge, it would open, and then it would say, well, the remote system is offline. And all the other 900,000 users, they can have a look at that circuit breaker before they even attempt to do the remote call and wait 10 seconds. No, they just have a look at the circuit breaker and see that it's open, and they can then give immediate feedback to their end user, reporting degraded capability of the system. The analogy with the circuit breaker in your house ends here, because whenever you want to flip it back on again in your house, that's a binary operation. It goes from off to on. But in software, you probably don't want to do that in a high volume system. So let's imagine what happens if the database becomes healthy again and you flip the circuit breaker back on again. That will cause probably a surge to the database of all those customers trying to get their information. Well, there's a good chance that you overload that just barely recovered database server or remote API server, and then it will get down again. So what you want to do instead is gradually increase traffic. So let's consider it like a dial, and then first you allow 10% of all traffic through, and then maybe 50, and then maybe 80, before going all the way back to 100% again. Then there's this outbox pattern. So instead of writing your data directly to a blob storage or a service bus queue, what if instead you would write it to a buffer first, and then all of a sudden it allows you to deal with outages in the remote system. So you do not directly write to a service bus queue, because whenever it's down you cannot perform that write operation. So if you buffer it locally first, and then in the background decide to start trying to send it to the actual service bus, then it allows you to deal with short-lived outages in the remote system. And this is what we also implemented for the non-critical data. So whenever we want to store things in blob storage or a message queue, it's by default in our system it's by default a operation that is not time critical. So we had some time to spare there. So we just buffered it first and then upload it in the background. Obviously we did add an alert to the buffer size, because if it takes too long for your messages to be processed, then there's an issue in the system as well. So make sure you buffer that outbox size so it doesn't grow too large without you being aware that the server bus is down, for example. Well, the leader election pattern, it's also very important in our system. So what we had was we had a requirement to process incoming messages in the order that they were being sent. So in our system that meant we could only have one processor for queue messages in one specific business case. That means that that's a single point of failure, and we already learned that having single points of failure is not a good idea. So what we did is we would have multiple instances of message readers, and we would have them compete for a lock, which is basically a record in a database. And the first one to acquire that lock in a transaction would be the elected leader, and that was allowed to process records. And the only demand that we had from that leader was that he would refresh that lock periodically. And that means that if that reader encounters an issue and all of a sudden, well, it stops existing, or maybe it hangs, whatever reason, it would stop refreshing that lock record. And that means that it will become automatically available after a timeout. And then at that point, one of the remaining healthy queue readers would step up and claim that lock again and become the new elected leader. And well, this helps by removing single point of failure from your architecture, and it allows you to have multiple instances of your software so it can still scale out. Well, you already saw that my front-end application did not crash entirely. It still allowed us to do some work. Let me show you. So this is the application, and I can still request injection or withdrawal. It will report an issue, but once the issue has been corrected, you can already see it is starting to process messages again. So the front end was not broken because the back end was broken. And this is what I mean with degraded performance. I already showed you the resilient HTTP client, so I'll skip that. Well, this is where I want to spend my weekend. So by adding all these safeguards, we were able to deliver a piece of software that was very resilient. It didn't have single points of failure, and whenever it was a big issue, we could transfer operations to a different cloud region. But in general, it's a very solid system, and we've had quite little issues with it over the past 2 years. So I'm really happy, and I have never had to drive all the way to the office, and especially in the middle of the night, to fix any issues. So everything could be done from home, and that's also greatly due to using the cloud and Azure DevOps as our platforms. So let's wrap up. DevOps, it means you build it and you run it. So you're not only responsible to create and build software, no, you're also responsible if it breaks down, and or maybe if there are any different issues. So you as a DevOps team, you are responsible to deal with any issue that may occur. Obviously, you can still work together with other teams in other disciplines, and then by doing this across the organization, you will have multiple teams which are autonomous but still collaborate to the greater good of the entire company. Well, in a mission critical system, always introduce redundancy. So never have any single points of failure. Build your system to expect failure. So it's like using that retry pattern, for example. So we expect our remote systems to be offline every once in a while. So we deal with that beforehand. So whenever there's a transient error, we can retry again. And if it takes a little bit longer, then we can use the outbox pattern instead. So we chose to use container clusters, which was a great help to us because it allowed us to scale up and down the system as demand varied. So it's quite easy to deploy new versions of the software, do some tests there before you really take it into production. It really helped us get a good sense of safety before delivering software into production, to test the release first. We automated just about everything. So not only the source code will be delivered automatically, but also the infrastructure, and even the failover was completely automated. So that eradicated a lot of human error opportunities. So, and just as a last point, do not have any single points of failure anywhere. A couple of useful patterns that we discussed are the circuit breaker, which protects your backend resource from surges, but it also protects your end user from long waits. So instead of every user having to find out that the system is broken, just one user needs to find out for everyone else to be able to be informed as well. The retry pattern can help you deal with transient errors. And the outbox pattern can help you deal with any longer lasting outages. And well, with that, I think we're through. So thank you very much for watching, and if you have any questions, please let me know. Follow me on Twitter or send me an email, whatever you like. Bye.